We have seen in the last couple of videos that if we are given one zero or one factor of a higher order polynomial, say a cubic, we can use the synthetic division to get a partial factorization, and once we get it down to a quadratic, then we're home free. We can either factor or use the quadratic formula. In the case where we have a fourth degree polynomial, we have to be given two zeros so that we can use the rational root theorem, use synthetic division one time to get it down to a cubic, and then use the other zero and synthetic division to get it down to a quadratic. So the big question then is, what if we aren't given one of those zeros or factors? How can we find one for a higher order polynomial, or two if we need it, so that we can kind of get the ball rolling and be able to find all the zeros and all the factors? And that's where the rational root theorem comes in. Now, the rational root theorem says that if a polynomial with integer coefficients has a rational root, which we know is the same thing as saying a zero, then it has to look like a fraction p over q, where p has to divide into the leading coefficient, and p has to divide into the constant, and q has to divide into the leading coefficient. So what that means is we're going to look for things that look like fractions, and the q's, the denominators, are going to come from the leading coefficient, and the p's are going to come from the constant. That is, they have to be things that divide evenly into the constant. So what this does is it gives us kind of a list of possible choices. So the p's, let me go back to green again, or the yellow rather. So the p's are things that divide into the constant evenly. So the things that divide into 3. So in this case, that would mean either a positive or negative 1, or a positive or negative 3. And that's it. The q's have to divide into the leading coefficient evenly. So in this case, that could be either 1 or negative 1, or 2 or negative 2. So that makes the p over q's, that is, the possible things that could be a zero for us, our possible choices to get the ball rolling are going to be, I'm going to take the p's over 1, so that means we're going to get positive or negative 1, positive or negative 3, positive or negative 1/2, and positive or negative 3/2. So it's a good news and bad news situation here. The good news is we have a finite list. We have 2, 4, 6, 8 possible choices. It's a third degree polynomial, so it could be that 3 of those work, or it could be actually that none of them work. So there is no guarantee that we have a rational root. Of course, it would be kind of a silly question for me to ask you, because if we can't do it, then I'm not going to ask you to do it this way. But I just want you to know that these are somewhat carefully constructed problems so that they do work. It might be that the only way we could find zeros is by using technology. That is, graphing this thing and trying to use our graphing calculator to approximate where it crosses the x-axis. But in this case, what we're going to do is try these different choices until we can find one that works. So this is the bad news part, is there may be a lot of trial and error involved. So I'm going to try first, say 1, and I'm going to put 2, 3, negative 8, and 3 as the coefficients. I'm hoping that we can find a 0 in this position. If so, then I'll be thrilled, because then we can get it down to a quadratic, and then we're home free because we can either factor or use the quadratic formula. If it doesn't work, then I'm going to just work my way through all the different possibilities. So let's see. 2, 2, 5, 5, negative 3, negative 3. What luck. We got one on the very first try. That isn't always going to happen, but that's good news, because now we have our partial factorization. that it's going to be x minus 1 times 2x squared plus 5x minus 3. And now we can factor this or use quadratic formula if we absolutely have to, but I think this one will actually factor. So you can do your box and diamond. I'm going to do my trial and error. I believe if I go a plus 3 there, that will be a 6x, and a minus 1 there will give us the factorization. So there is our factorization, and our zeros are going to be what makes these equal to 0. That's going to be a 1, a positive 1/2, and a negative 3. Now, this was nice because it worked on the very first try, but as you might imagine, the bad news is we might have tried, we might have gone through this whole list before we found one that actually worked. So let's try a new example, and we'll see how that one goes. So let's say here we have p of x this time is going to be x to the third plus x squared minus 8x, and then a plus 6. So we're going to go to our p's and q's. That is, what are our possible p over q's? So p, remember, divides into the constant, so that could be a plus or minus 1, a plus or minus 2, a plus or minus 3, or a plus or minus 6. The good news in this case is that the q's can only be 1 or negative 1. That's what divides into the leading coefficient evenly. And so this is our list of potential zeros, possible zeros. And we're hoping that we can find at least one of these that works. So, like we did before, I'm going to try 1. I'm going to put the coefficients across the top here. And we've got 1, 1, 2, 2, negative 6, negative 6. I guess we're learning that 1 always works. I don't think that's always going to be the case. So here we've got a partial factorization, x minus 1, and now the bad news is that I don't think this x squared plus 6x minus 6 is going to factor, so we're going to have to use the quadratic formula. So we're going to get negative 2 plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's going to be a negative 2 plus or minus, and let's see, that's going to be 4 plus 24 is 28. We can simplify that by splitting this apart, negative 2 over 2 plus or minus. We can simplify square root of 48, or I'm sorry, square root of 28, because that's 4 times 7, and the square root of 4 is 2. So we can reduce that further and say that negative 2 over 2 is negative 1, plus or minus the square root of 7. So our zeros are going to be the 1 that we got on the first try, and then negative 1 plus square root of 7, and negative 1 minus the square root of 7. Our factors now, I have to be a little careful how I write this, so I'm going to say our factors. I keep trying to say f of x by force of habit. One more time. So our factors, if I can get my pen to cooperate, factors, we're going to say that p of x is going to be x minus 1. Then I'm going to go x minus that negative 1 plus square root of 7. And I'm going to go x minus the negative 1 minus the square root of 7. Let me clean that up a little bit and get that p of x is going to be x minus 1, x plus 1, distributing that, minus the square root of 7, and x plus 1 plus the square root of 7. So there are the zeros and factors for our polynomial. Okay, let's try another one. This time we're going to say y is equal to x to the fourth minus x to the third minus 29x squared and minus x minus 30. Now the bad news here, there's quite a few choices for our p's, because our p over q, remember the p is going to come from what divides into 30 evenly. So we're going to get, for the p's, there could be 1 and 30. There could be 2 and 15. There could be 3 and 10. There could be 5 and 6. And I think that's it. The good news is we get only plus or minus 1 for the q's. So our p over q's are going to be this big list right here. Now, maybe more bad news, I don't know. Because we have a fourth degree polynomial, we are going to have to find 2 zeros, because the first one's going to take the fourth degree down to a third degree, but then we have to find a second one to get that third degree down to a quadratic. And then once again, once we get to a quadratic, then we're going to be home free, because even if we can't factor it, we can go to the quadratic formula. All right, well, let's see how quickly we can find our first one. So we go 1, 1, 0, 0, negative 29, negative 29 times 1, negative 29, negative 30 times 1, negative 30 is negative 60. That's no good. So, but it looks like we're kind of close. Let's try maybe a negative 1. And we'll go 1, negative 1, negative 29, negative 1, negative 30. Remember, we're trying to get something that will make the remainder 0. So I'm going to go 1, negative 1, negative 2, positive 2, negative 27, positive 27, and 26, negative 26. Oh, nope, that's not going to work either. So we got to try something else. We can try 2 and go 1, negative 29, negative 1, negative 30. And let's see, 1, 2, 1, 2, negative 27, negative 54, negative 55 times 2. No, that's not going to work either. Well, this is the bad part about rational root theorem. The good part is it gives us a finite list of possible candidates. The bad news is it can be a long finite list. And so let's see, we're up to 6, so that's going to be a negative 23 times negative 2 will be a positive 46. That's going to be 45 times negative 2, not going to work. So let's see, how about 3? So I'm going to go 1, negative 29, negative 1, negative 30. And let's see, we got 1, 3, 2, 6, negative 23, negative 69, negative 70. Nope, that's not going to work. How about a negative 3? 1, negative 29, negative 1, negative 30. Let's see. We are going to get 1, negative 3, negative 4, 12, negative 27. Nope, negative 17. Try that again. Negative 17 times 3 is 51. And let's see, that's a positive 51, so that'll be a 50, and that's going to be negative 150. Nope, that's not going to work. Let's try maybe negative 5. I just got a feeling. And if we put negative 5 up there, we've got 1, negative 29, negative 1, negative 30. And that's going to give us 1, negative 5, negative 6. That's going to be a 30. That's going to be a 1. That's going to be a negative 5. And that's going to be a negative 6 times negative 5 is 30. Hooray, there's one that works. Now, we have to find another one, because now this is still a cubic at this point in time, which we still can't factor. Something to be careful of. If one works, you should usually try to do that again, because it could be that it's a double root. That is, could have multiplicity 2. and it should be a shame to get through the whole list, not find anything else that works, and then come to realize that we really should have tried that one again. 55, 56, this is getting huge, that's too big, so let's go back to our 1, -1, -29, -1, -30. I'm sorry, let's go back to what we got after we got the first one that worked. So I'm going to go back, I'm going to change color so we can keep track of it. So we've got the 1, -6, 1, -6. Those are the coefficients we got from that line. And let's try this times 6 and see what that does for us. That's 1, 6, 0. 0 times anything is 0. 1 times 6 is 6. And sure enough, that worked. So now what we have is our partial factorization. So far we've got p of x is equal to the x plus 5, because the -5 gave us a 0. And then we've got an x minus 6. That's from that last one we got. And then the coefficients across the bottom are going to be x squared plus 0x plus 1. So the remaining factors are going to come from x squared plus 1. But this is a sum of two squares, and that isn't going to factor. But if we solve that, when we square root both sides here, we're going to get x is the plus or minus, the positive or negative, square root of -1, which we haven't seen in a while, which is I. So what this means now is we're going to allow complex numbers, because our fundamental theorem of algebra says that we'll get n, in this case 4 zeros, if we allow complex numbers, imaginaries. So we're going to get our -5, the 6, and then I and -I are all the zeros, which is going to make our factors. I'm going to come down here a little bit so I have a little bit more room. P of x is going to be x plus 5, x minus 6, x minus I, and x plus I. Whoa, that's crazy. I'm going to stop here on this video, and I'll do a second part to it.